so far this semester, the sounds we've been creating are all of a generative nature. Oscillators, filtered noise, playing back a sound file that's been loaded into a buffer from your hard drive. So different types of sounds, but in all of those cases, the process is inherently generative. Some sound is generated, some digital signal is created, and out it goes to our speakers. And this is fine for a lot of cases if you just want to sort of generate a bunch of sound and send it to speakers. There's really nothing else you need to know other than just how to build a synth def and create a bunch of synths, maybe using iteration and things like that. But this is not always sufficient for what we want to do. In a lot of cases, we want to have maybe a bunch of generative sounds or source sounds, and also create a bunch of processing synth defs, which apply delays, reverbs, pitch shifting effects, all sorts of interesting techniques for modifying the sound. And although it is technically possible to build these effects into the same synth def that contains the generative code, you can probably imagine that those synth defs become really big and bloated and difficult to deal with. It's possible to make a piece which just has one synth def which kind of does everything, and you just have to send it many, many, many types of set messages. But it's an anti-modular approach, right? Imagine if you had, I'm trying to think of a good example here, like a modular synthesizer, but all of the modules are permanently connected together in a very specific way so that you can only, it's easy to use, but you have a very limited set of options. So it's a rough analogy anyway. Usually it's preferable to make many, many different synth defs which represent modular tasks, like applying a reverb, applying a delay, generating a tone, things like that. And in the world of audio, hardware, software, analog, digital, there is always a signal flow. And when we say signal flow, we're talking about there's a point of origin where some sound is created, and it follows a path, usually going through device and device and device in some specific order so that the signal is modified in certain ways. Like in a PA system, you have a microphone, a preamplifier, a mixer, an amplifier, and speakers. And you can't just take these devices and connect them any old way you like. They have to be in a very specific order in order to produce the specific result that you want. DAWs are just like this, right? You have insert effects that you can place on a channel in a specific order, and those inserts occur in that order. You can also establish auxiliary sends, and so there's a signal flow in every audio context, and SuperCollider is no exception. So when you have a sound which generates some signal and you want to apply some reverb to it, you have to manage and be aware of the order in which those processes reside on the server. And so to get started, I'd actually like to start with a diagram. In SuperCollider, when we boot the server, actually I've prepared some code ahead of time just to save some time. So we'll boot the server, and s.plotTree. Alternatively, you can say server show node tree. These are the same things. This line of code brings up a little window that says localhost node tree, and I'm going to resize a few things here. And this window represents the status of the server. And I think we've touched on this a little bit. The little white rectangles are synths, and the gray ones are groups. And the synths and groups are both types of nodes, N-O-D-E. A node is an entity which lives on the server and at a specific location relative to other nodes. These white synths are just a result of having the level meters open. So it's sort of no need to get distracted. Just know for now that this is a graphical representation of the processes that are alive on the server. And I'm going to draw a version of that over here. How does he draw such straight lines? Years of practice. No, I'm kidding. You hold shift. So this is going to be scsynth, the audio server, the process that handles audio in SuperCollider. And so there is always a signal flow, and on scsynth, signal flows from head to tail, or in other words, top to bottom. So the head of the node tree is at the top, and the tail at the bottom. Right? So signal flows in this direction. Right? So also, when we've been building synths, we know we have to include, if we want to generate a signal and send it somewhere to speakers or to an effect, we have to put an out in that synth. And so out is the UGen, which writes a signal to a bus. And the concept of a bus is a little bit elusive. A bus, at least in the context of SuperCollider, and kind of more generally, a bus is simply a place, a location to which signal can be written and from which signal can be read. It's a location where audio can exist, where multiple processes can basically share it. One, generating it as an output and putting it on the bus, and another using that signal as an input by reading from the bus. And in SuperCollider, there are audio buses and control buses. So audio buses are for sending and receiving unit generators that have an AR, right, audio rate signal, and control buses are for control rate signals. They work the same way, but they're completely separate. In this lecture, we're just going to focus on audio buses, but the concepts are completely the same from very, very, very minor differences between audio buses and control buses. So when we boot the server, by default, a bunch of buses are created for us. And we can see how many audio buses there are by typing s.options.num audio bus channels. And the default at the time of giving this lecture is 1024, which is a lot. And I also sometimes like to think of audio buses as like channels on a mixer. And mixers have like 16 channels, 24 channels, maybe 32. And so the server is kind of like a gigantic mixer with 1,024 channels. And you're basically free to use these buses, or these bus channels, however you like, for passing signal and writing signal and reading signal, and just generally using them however is relevant for your work. By convention, when we boot the server, there's a contiguous block of buses starting at bus number 0, so at the very beginning of the buses, which correspond to the hardware outputs of your sound card or audio interface. And then after that, there's another contiguous block of buses, which corresponds to the hardware inputs on your audio interface or sound card. And by default, it's 2 outputs and 2 inputs. You can change this. It's totally customizable. But then the remaining 1,020 buses are just audio buses for internal routing and using them for whatever you like. And I'm going to draw these buses as if they are, I think a way that makes sense is to draw them as downward arrows. Right? So we're just going to draw some buses here. I'm not going to draw all 1,024. We'd be here all day. But I am going to draw, I don't know, like 8 of them or something. Okay, so bus 0, bus 1, 2, 3, 4, 5, 6, 7. And these go on all the way up to 10,024. So by default, these 2 down here are hardware outputs. These are speakers, left and right speakers, right? So it's assumed, and it is usually the case, that for instance, I'm connected to HDMI, and HDMI is my output device, and so 0 and 1 correspond to the first and second channels on this mixer, and out they come off speakers. And then the next 2 are inputs for microphones and synthesizers and other analog equipment that generates a signal. You want to plug it into your interface. So here we have a little microphone. Maybe we've got another microphone over here. Right? Okay. So these 4 at the beginning are kind of considered reserved for that purpose, but 4 and above, use them however you like. Okay, so what we are accustomed to doing so far is just making synths and then plunking them down on the server and saying out 0, right? Go to speakers. So I have 2 synths here. The first is called Sine, and the sound source is a sine wave, and the frequency is a constantly changing random value between 150 and 4,000 hertz. There is a trigger envelope, which is a very short percussive envelope that does not have done action 2, and it's being re-triggered using dust, which is just a UGen that generates random impulses with some density of pulses per second. So it's approximately 6 triggers per second, and it's a 2-channel dust, so an independent dust in left and right. And then this is an overall amplitude. It's an attack, sustain, release envelope with a gate, so it just holds itself open with a 5-second fade in and a 5-second release. And then we apply these envelopes as well as an overall amplitude scaling. So this one sounds like this. We can close the gate, and it fades out. This next one is pretty simple as well. There's pink noise. Its amplitude is being modulated by a pulse wave that's running pretty slowly. So we just get like a kind of burst every approximately a half second, a little bit faster than that. Again, there's an overall envelope, and so that one sounds like this. These are not particularly interesting sounds, but they are good for hearing whether or not reverb is present, because they just get in, they have a very short attack, short release. So I've picked them because they work well with reverb. All right, so when we make a synth like this and make a synth like this, they go and live on the server. And there they are. So pink noise is at the head of this default group, and then right after it is the Sine synth def. So they have an order, right? And we'll fade them out, and you'll see they disappear after 5 seconds or so. So in this case, because these synths do not rely on each other's signal, they're completely independent. They both just go to bus 0. It doesn't really matter what order they are on the server, right? So here we have, this is our sine wave, and this is our pink noise. And they both have an out, and we have specified on synth creation that their output destination should be 0. And so what happens here is this synth writes to bus 0, and this one writes to bus 0. Now, technically, both of these are stereo signals. You can hear there's both channels. Both of these have exclamation point 2 things in them, so it actually expands into a 2-channel signal. So when we say bus 0, the lowest channel of this 2-channel signal goes to bus 0, and the server says, oh, I've got more channels, so I'll just put it on 1, and okay, I'm out of channels, I'm all set. So it just assigns additional channels to ascending incrementally higher buses. So I guess if we want to be very specific here, we could draw, another arrow here, like it would come out of here, and it's going here to bus 1. It's not really the focus here, but just be aware that both of these go to bus 0 and technically bus 1 as well. So how does the server actually compute these samples? And this is something that not just SuperCollider does, but pretty much every digital audio software does. Audio samples are computed in blocks. So a block of samples, a block of samples, a block of samples. And you can configure this. It's usually a power of 2, somewhere between, I don't know, maybe 8 at the smallest, and like 1,024 blocks, maybe even larger. And in SuperCollider, you can see the block size with s.options.block size, which is 64. So when we play sound, when the server is alive and processing synths, it's calculating the output of those synths 64 samples at a time. Of course, it's doing it incredibly fast, right? It's zipping through 64, 64, 64. But on each individual pass where 64 blocks of samples are calculated, the server goes from head to tail. So at time 0, the first synth it encounters is this sine wave synth. So it says, okay, let's see what comes out of these UGens and how they're interconnected. And there we go. I've got my next 64 samples. And so it just sets them out on bus 0. And then it continues moving down, and it encounters this pink noise synth def. It says, okay, let's calculate 64 samples out of U as well. It gets 64 samples, dumps them onto these 2 buses. And the default behavior when two signals are being written to the same bus is to mix them. In other words, just sum their sample values together. So these two samples exist, and then a microsecond later, another stereo signal is added to the same pair of buses. And because A plus B is the same as B plus A, it does not matter, whether we add this one first or that one first or what order they're in. So that's why we can just kind of, we want to play the pink noise first, that's great. Sine wave first, that works too, doesn't matter. So when we have a synth like this reverb over here, we need to be careful that the reverb is downstream or sort of, towards the tail relative to any source synths that are going to be flowing into this reverb. So what happens here, just briefly walk through this reverb. We've got an input bus argument as well as an output bus argument, because this reverb is going to be reading from a bus. So that's why we're using in, and the two arguments are the bus to read from and the number of channels. So for example, if this was like 4, and like if we said 4, 4, then this would say, okay, I'm going to take a look at 4 and grab 1, 2, 3, 4 channels. It would read 4, 5, 6, and 7 in that case. Right? So we want to read 2 channels, and this is, I cannot stress this enough. When you're working with inputs and outputs and buses, you have to be mindful of your channel size at all times. If you make a synth and it outputs a stereo signal, and then you instruct some other synth to read from that bus, but only read 1 channel, then you are just not catching your second channel, and so you're just pulling in a mono synth. Similarly, if you are writing a 1-channel signal to a bus and tell it to read 2 channels, it's going to grab that extra channel, and who knows what's on that bus, right? It could be something else. So it's generally it's a pretty safe environment. You're not going to blow anything up, but you just have to be aware for every synth def. Does it have an input? Does it have an output? How many channels is the input? How many channels is the output? This is fixed information. You remember how when we have play buff, we have to put a hard number for the number of channels for play buff. We have to put 1 or 2 or something else. Can't be modulated. So you've got to, when you're imagining your signal flow in SuperCollider, you must make concrete in your mind the number of channels for every unit in the signal flow. Right? Can't dynamically change. You can always do something like make like a 16-channel synth, but then like set certain channels to amplitudes to 0 and effectively kind of turn off certain channels. But in that case, it's a 16-channel output, even if some of the channels are silent. So there's really no way around it. So we read 2 channels in because we know we're sending 2 channels out. And Freeverb 2 is what I've chosen here. Freeverb is a very simple reverb. I don't think it sounds super fantastic, but it certainly works. And Freeverb 2 is a little bit like Balance 2. It expects a 2-channel input signal, which we've called sig. So we've got to split it up into left and right and feed them into Freeverb 2. And then we have a bunch of parameters. All 3 of these mix, room, and dampening are on a scale of 0 to 1 for simplicity. So 0 means all dry. 0 means all dry, no wet. And 1 means no dry, all wet. And I'm saying all wet, so just the reverb signal coming out of here. Room, this is room size. I don't know what 1 means in like meters or square meters or cubic meters. It just means a big room. So I put 1. And then dampening is basically a low pass filter. The closer you get to 1, the more high frequencies will be filtered out. And then I have a mul, like most UGents, they have a mul value, and I'm setting it to an argument called wet amp, which is 0.3 by default. And then summing the original input signal with this fully wet reverb signal that's been scaled down here. And so it's this particular synth def basically takes the signal in, on the side processes some reverb and adds it back in. So we hear the dry and the wet with a particular balance, and out it goes. So what this looks like here on our, let's see if we can undo a bit. What we want is this sort of situation, right? Reverb downstream. And so the flow here is we have to pick some bus that's not 0, 1, 2, or 3. Let's just arbitrarily say 6, right? So we tell this synth to output to 6, technically 6 and 7. And then we tell the reverb to read from 6 and 7. Right? And then this goes out to bus 0 and 1. Okay? So this works fine because nodes are processed head to tail. And so first, the 64 samples of this sine wave are calculated and dumped onto 6 and 7. So there they are. They exist in this sort of mid-cycle moment. And then we get down to the reverb, and we say, reverb, read from those buses, do your thing, and whatever you send out, put it on 0 and 1. Right? The reason it doesn't work if these are in the wrong order. So for example, if we do this, if we say reverb, even if we have our buses configured correctly, we say you go here. Actually, no, first read from 6 and 7. Right? And then we tell the sine wave to write to 6 and 7. Right? This is the wrong order. So on a particular cycle of 64 samples, SuperCollider says, okay, reverb, read from 6 and 7. Of course, there's nothing there, right? There's nothing on 6 and 7, so silence comes into the reverb, and silence gets put back out onto 0 and 1. And then the sine wave generates its sound and puts it on the bus. But of course, it's too late, right? The contents of 6 and 7 have already been read. And at the end of each cycle, all of the buses are zeroed, right? So the data does not remain on the bus at the end of one 64 cycle sample. So we get to the end of a 64 sample cycle, and everything gets multiplied by 0, right? So all the buses get wiped, and we start again for the next 64 samples. So if they're in the wrong order, the result is silence, right? Because you've got your order mixed up. So let's just see how that works. What we're going to do here is I'm going to say reverb. And for the input, sure, let's go ahead and do what we were doing. We'll say it's going to read from 6 and out to 0. And we've set it up to read 2 channels, so it's actually going to read 6 and 7. And because it's a 2-channel signal, it's going to go out to 0 and 1. And then we'll grab this. Sorry, out 6. Right? So this should work. I know it looks like I put them in the wrong order, right? Because I did the reverb first and then the sine wave. But this is actually correct because of the default behavior of how synths are added to the server. Okay, so now we can say, and I should have this open as well. You can see sine is at the top, reverb is at the bottom, and we just faded out the sine wave, and now all we have is the reverb, and we can just free that at leisure. Right? We're accustomed to this kind of statement. We're going to make a synth, we're going to give it a global variable name of the synth and an array of argument values. But there's actually 2 additional arguments in a synth.new call, and they are target and addAction. And together, these 2 values instruct the synth on where it should be placed on the server. So the default target is the default group on the default server. Right? So the default server is really the only server we've got. It's the one that's running right now on this computer. And the default group is this gray box. Right? And it's so the synth is, when we play a synth, it gets added to this group. We'll talk about groups in a second, what a group is and why we use them. But this default group always exists for convenience for us. And the default, so this would be s.default group. Right? This is group 1, right? There are other options for targets, but for now we'll stick with this. And the default the addAction is one of several symbols. And symbols are, give myself some space here. We've seen symbols before. This is a symbol, this is a symbol. And so the default is add to head. And this means add this synth to the head of this target. And this target is a group, so it's going to be put at the head, the very top of this group. Okay. And that's the default. If we got rid of these two values, the behavior would be the same because these are the defaults, basically. So there it goes. And then if we make our sine wave synth and tell it to go out, group 6, and if we give these same defaults, it will get added to the head of the default group, placing it above the reverb. And that's the order we want. Which means if we run these in the wrong order, which kind of feels like the correct thing to do, making the sound source first and then making the effect, it doesn't work because the sine wave gets, oh, hang on, command period, get all this stuff out of here. Sine wave first, it gets added to the head of the default group, and then the reverb, and we get nothing. Right? They're both running, they're both writing and reading from the correct buses, but the order in which they exist on the server is incorrect, and therefore they can never actually talk to each other and share information. So you have a variety of options, a colorful variety of options for how to specify the placement location of synths. Let's see if I can actually find the addActions. There should be, I think it's in the, in the synth help file. There's a little bit of an explanation for what the target can be. It can be a server, a group, or another synth. Actually, I think the default is nil. The default is nothing, and when that's the case, it defaults to the default group of the default server. Right, if it is nil, uses the default group of the default server. But it can be another group that you've created, another synth that you've created. And the addActions are add to head. So this is in this case, the target should be a group, and it gets put at the top of that group. Add to tail, in which case it gets put at the bottom of that group. Add after, which places the synth immediately after whatever the target is, a group or a synth. Add before, the same as add after, but before. Add replace, a node will replace an existing node. And these are the 5 options. Add to head, add to tail, add after, add before, add replace. Now, it doesn't matter how much after something is in something else, right? You can have your sound source way at the top and a bunch of stuff in the middle and your effect way at the bottom. It'll still work, right? It just has to be after. So here are a couple of ways you can do this. We might want to make our sound source first. So we can just actually place it right on the server. Right? Just forget about the target addAction. There it goes, head of the default group. And so then we have a couple of options for the reverb. We can say this synth is the target and add after. Right? So we say your target is this synth which already exists. There it is. And you are going to be placed directly after it. And that works just fine. s.freeAll is kind of like command period. Just remove everything on the server, right? And back it goes to its default state. Another option is we can make our sound source and then place this after the default group. So the target is now not the synth, but the group that it lives in, and we're going to add after there. And it actually gets put after the group. Yeah? Let's see. Let's talk about groups for a second, right? It can be, if you have a lot of sources and a lot of different effects, you'll find very quickly that it becomes really clumsy and annoying to deal with them all in one gigantic group, like a group containing hundreds and hundreds of synths, right? So my personal preference here is to actually create groups that are in the correct order. And a group is just like, it's just another one of these. It's a unit on the server that can contain other nodes, groups, and synths. You can have any number of subgroups within subgroups. And so let's make a source group, group.new. And again, these group.new has target and addAction, and the defaults are the same. So when we make a new group, if we don't specify otherwise, it will be added to the head of the default group. And then we can make a group called FX group, which is going to be, the target is source group, and the addAction is add after. Yeah? So we've made another group, and it's placed immediately after the source group. And so now it really doesn't matter what order we add these synths as long as they are placed in the correct groups, because the groups kind of take care of the order. Everything in the source group will be before anything in the effects group. So all we have to do is say you go in the source group, and you go in the effects group. We can even just add these, simultaneously. It doesn't even matter if we do, we could switch the order. It does not matter because they're going in these two groups. So groups are a very handy tool for organizing your signal flow. This is a very simple example where we just have one effect. And so we're really just going to have one reverb effect in this tail group. And then we can dump anything we like into the source group. And as long as it is writing its signal to the buses that the reverb is reading from, then the signals will connect, they'll be in the right order, and everything will have the same reverb effect applied to it. Groups can be freed, just like synths. S.freeAll would destroy all groups and synths. And there's a very nice little trick, actually. This is another convenience of using groups. Let's say you have 100 synths. Different parameters, but they all have a gated envelope. And so all these 100 synths are living on the server, and you want to turn them all off. Right? And I don't want to have to say, okay, synth0.set, synth1.set. Iteration is helpful here if you've stored them in an array. But if not, another option is to make sure they're all in the same group. And then you can talk to the group and set the parameter of the group as if it were a synth. And the group's response is to pass that message into all of everything that it contains. So if there's a synth inside of that group, it receives the message. If there's a group inside of that group passes the message inside of it, and so it kind of propagates inward. So for example, if we, let's copy this, and I'm going to make the reverb synth. This doesn't work because I destroyed this group here, so we'll make it again. We're going to do a slightly different approach here. We'll say just make the effects group. Forget about the source group, right? We actually don't really need that. We can just say. So now, I'm just going to make a bunch of these manually, and I'm going to say. Your target is the effects group, but your addAction is add before. So they will all be added before. Oh, I need to make the reverb too, of course. Okay. Yeah. And I can just make as many of these as I like. Oh, no, I'm doing this wrong, because now I'm not putting them in a group. So I can't talk to them all at once. I guess what I could do is s.defaultGroup.set. And that works. This gate message is also passed to the reverb synth, but it doesn't have a gate argument, so it's harmless. I think what I probably should have done is just stick with my original plan here and just make two groups like this. Command period first. So we make our groups. reverb goes into that group. And now we can make a bunch of these synths that go into the source group. And then we can say source group set. And it's a very nice way of talking to everything inside of that group. That message gets passed inside, and so any synths inside that group or any of its subgroups will receive that message. So this is a common approach I use when I'm composing a piece which is a little bit more complex in terms of signal flow. I plan it out. I make a sort of flow chart for myself, and I say, what effects am I using? Are they going to be sort of parallel processing, so a signal branches and gets sent to two different buses, or is it going to be like daisy-chained, one after the other? So I map out how many buses I need and how many channels those buses should be, how many groups would be convenient to allow me to manage everything nicely. As I'm working, sometimes I just dynamically add more groups to the project because I feel like I need them. But the groups are, I think, really the best option for organizing the order of synths. Is that as long as the groups are in the correct order and you add synths to the correct groups, you basically don't really have to think about it anymore. Okay. Is that sort of clear, the general concepts here? Okay. I'd like to now turn our attention to the fact that I've been just arbitrarily using bus 6 and just specifying 6, 6, 6, 6, 6. And you can probably imagine that if you have a complex project where there's lots of effects and lots of buses, it's stupid to have to remember, okay, bus 6 was reverb, and then I think that was 2 channels, and so I think, and then you're having to like remember which is which, and maybe you have like dozens and dozens of buses. And numbers are not very meaningful when it comes to remembering what they're being used for. And so that is why the bus class exists. And basically it allows us to name a bus or a contiguous block of buses, just in the same way that we name these groups and these synths. And so, for example, we'll call this FX bus, bus.audio. We want it to be an audio bus, and it's going to belong to the server that we're using. So we give it the name of the server and the number of channels that we want. We've been working with stereo signals, so there we go. And you can see in the post window that it's an audio bus. The index of the lowest bus the lowest bus index in this allocation is 4, which makes sense because we know that 0, 1, and 2, 3 have been set aside for hardware purposes, and so the first available bus index is 4. And we asked for 2 channels. We got 2 channels, and this is the name of the server on where this bus lives. Now, it's important to remember, I guess it's useful to remember, that this expression does not actually create a bus. These buses already exist. When we boot the server, those buses come into existence, and they're just ready to go, right? They don't have names or anything. They're just numbered. All we're doing here, instead of creating a bus, is we are creating a name on the language, in the SuperCollider language, that allows us to refer to a specific bus or set of buses. And so now we can, with this bus available to us, we can make these groups. And I'm just going to actually put these all in the same, oops, I think I evaluated something by accident. So we make the reverb, and we'll make the synth. And instead of this, we're going to say FX bus. Right. So just making sure there's nothing there. OK, and don't need 2 of those open. So now I should just be able to run this, and right, it all just works. So we've arrived at what I think is sort of the robust and well-structured way of creating a simple signal chain, giving things appropriate names, making sure everything's in the right order. We make a pair of groups with a specific order. We create synths, place them in the correct groups, and use a named container to refer to the bus that they share. A couple of, so if we were to allocate another bus, we'll say extra bus, don't really have a purpose in mind yet, you can see that it grabs the next available bus. We've already used 4 and 5 because we wanted a 2-channel bus, so 4 and 5 are spoken for. Doesn't mean we can't explicitly say write this to bus 4 using the number 4, but this is kind of the whole point of the bus object, is it handles the allocation and referencing for you. So it remembers that we asked for a 2-channel bus, and it says, okay, you already took those, so here's the next available pair. And if we're really careless and run this multiple times, we're using the same named container, but we're starting to exhaust our bus supply. And if we do something intentionally very stupid, like this, just allocating, 1,000 stereo buses, then this will happen. And it says error, failed to get an audio bus allocated. Because there's only 10,024, and we're asking for 1,000 stereo buses, which is 2,000 channels. It doesn't have that many. So it says you have run out of buses. You should use the ones that I allocated for you instead of being careless. So if you run into this situation, the way to reset the bus counter is s.new bus allocators. And this, remember, we're not creating or destroying any buses here. The buses exist. There's a fixed number of buses. We're just creating a system that makes it easier for us to refer to those buses. And all this does is reset the language side counter. And so now if we allocate our effects bus again, you see we start back at 4, extra bus is 6. And so this expression, I frequently place this, if I was going to use this code to as my performance setup code or something like that, I wouldn't just put effects bus here. This is okay, it works, but if I hit command period and do it again, and again, and again, eventually you can see we're getting up there in bus count. So I always put s.new bus allocators right before I allocate buses, so that whenever I run this code, the first thing I do is reset the counter and then allocate buses anew. You don't even need to do this multiple times. You could do this just once, right, and then never come back to it again, because that bus has been, that's secure. It exists. It's got a name. Command period does not destroy buses and does not undo your naming scheme. So this is all fine. Right? The bus is still there. This will have meaning until we explicitly overwrite it with something else. So I think that's actually everything I wanted to cover today. These principles extend very easily to other types of effects, other types of source sounds, signals which are more than 2 channels or just monophonic channels. As long as you are consistent with the number of channels being passed in and read out and the number of channels being allocated for each bus, then everything should just sort of work. I guess there is one more thing which I tend to do, and as you can see, this works fine, right? Although the process of creating nodes, groups and synths on the server is not instantaneous. Just like reading a buffer, reading an audio file into a buffer is not instantaneous, and adding a synth def is not instantaneous. There's a bit of communication that needs to take place between the language and the server. And this I think, I've never seen this kind of fail, but I think it is theoretically possible, depending on your configuration. Maybe you're sending over sort of a network to somebody else's server, and I don't think the order in which these statements appear guarantees the same order that they will arrive on the server. So for example, if something caused these two to switch, then this doesn't work, right? Because if this is first, it tries to add after a group that already exists, but of course it doesn't already exist. And so the way I guarantee the order of these is by bundling these together into one message, so that it's sort of it's guaranteed that these will all arrive at the exact same time, and will be the way we do this is s.bind. This is a habit I've gotten into. This basically, the way when you make a synth or add a synth or read a buffer or do anything in the language that involves doing something on the server, under the hood, what's happening is the language is sending one or more OSC messages to the server. OSC is a communication protocol designed to work over networks. And so we have this high-level sort of language of synth.new, group.new. We can just very clearly say what we want, but then a bunch of OSC messages get generated. And s.bind ensures that the generated OSC messages from these expressions are bundled together into one OSC message. And so this is, that didn't work because, yeah, I think I had something highlighted maybe, I'm not sure. But yeah, just once we do s.bind, it's just like a little extra insurance, a little safety measure. I don't think it's really required, and I don't think I can truly say that I know all the details of under the hood and exactly what's going on, but it's a habit I've gotten into. All right. So the homework for this week is it shouldn't be too much work. I think it's really just like 3 or 4 questions where I'm going to give you synth defs. I'll give you a source synth def and one effect and another effect, so 2 effects. And then I ask you to basically build a little architecture which follows a specific routing paradigm. You've got to go source through effect A through effect B to speakers, source B to A to speakers, and then I also want you to make a pair of buses so it goes to A and also to B, and then both of those go to speakers and get summed together like that. So effects in parallel, effects in series in either order. It's basically that. So you'll have to use the concepts here and kind of expand on them just a little bit. So I think that's going to be it. So that is it, and we'll see you next week, and stick around if you have specific questions.